2.5 is on what's called special integrating factors, and it's kind of more generalizing the integrating factor concept we looked at in the previous section. So we're going to just pretty much jump into the definition, theorem, and then look at examples. We won't spend a lot of time on theory in this stuff. There's a number of just kind of get it done topics in 2.5, 2.6. So let's take a look. So definition 3, let's write this down. If the equation, and this is familiar, mxy dx plus nxy dy equals 0, we'll call that equation 1, is not exact, but this equation is exact, then, so right, basically what you're doing is multiplying by mu of xy, which is what we did before, right? But this is a more general case, basically. So then this is an integrating factor. So write all that down, and we'll label these equation 1, equation 2. So if that's the case, then mu of xy is called an integrating factor for the equation 1. So here's the theorem of how to find it, or what it is. So this one says if, and then just kind of, it's a difference and then a quotient. So it's like if the partial m partial y minus partial n partial x over n is continuous and depends only on x, then, and give yourself some room here, mu of x equal to e raised to that whole partial. So that's partial m partial y minus partial n partial x all over n, oops, dx. So dx is not, yeah, no, that's right, dx is an integrating factor for that equation 1. So is an integrating factor for that equation. Also, or similarly, you know what, let's move this over. Move this down a little bit like that. Okay, next one. Same kind of statement. This will change now. And you have if partial n respect to x minus partial m respect to y over m is continuous and depends only on y, then it's the same mu of x, then mu of y, sorry, same mu, so mu of y equal to e raised to the integral of partial n partial x minus partial m partial y over m dy is an integrating factor for the equation. So is an integrating factor for 1. It basically tells you how to find it. So we'll be doing that, but this is really the method we want to look at to do it. So let's take a look at the method. So this is what we would say is the method for finding mu of x or mu of y. And let me highlight that or something. Okay. Okay, so then if m dx, and those are functions of x, y, but in dy, it's a little easier to write it this way, equal to 0 is neither separable nor linear, compute partial m respect to y and partial n respect to x. If they're equal, what do we know? If partial m respect to y equals partial n respect to x, then the equation is exact, and you solve it in the exact way. And then the equation is exact. If not, then we consider the stuff above, the mu above. Then consider calculating this. Then we do that calculation, partial m partial y minus partial n partial x over n. So we got to check that though. So if only a function of x, then mu of x, and it's the same one above. So this mu of x here is an integrating factor. Okay, so then, is an integrating factor. If not a function of x, then you look at the other one, essentially. Okay, then consider the other case. So the other case was partial n respect to x minus partial m respect to y over m. And then if only a function of y, then mu of y is an integrating factor. So same statement. So if only a function of y, then your mu of y. Now you got to do the calculation, right? You got to actually calculate mu as above. So then the other one, as described above, so this one is an integrating factor. Okay. So I didn't obviously go over any like reason why this works. Okay, so you can check it out if you want. Just like in the calculus level, calc books, you kind of have to wade through and see what to show and what not to show. I think at this stage we got to just keep on plugging on. Now it's time to look at some examples to apply this. So number 8 and number 9. And that's all I got for this section. So I think we'll stop and do examples in the next video. Keep them shorter.